I want to talk a little bit about the small signal model and using it, particularly about transconductance. So if we had a common source amplifier, and we've got this resistor load, RD here, and the small signal model simplifies as just this for a MOS transistor. This makes it very easy to find the input and output resistance and the gain. So we have R in, we have R out. That's from the standpoint of the load, which we don't have. And then we have an overall gain. And so R in is just infinite because it's an open circuit here on the gate. And R out is just R naught parallel with RD. If we ignored R naught, then it would just be RD. And then the gain, not going back to the signal generator, but just back, but including the input resistance, which is infinite, is just minus GM R naught parallel with RD. So it's very easy to calculate and find that. And R naught, of course, is VA over ID prime, and that equals VA prime times the channel length L divided by ID prime. Remember that ID prime is just the gain that you get by using the saturation equation. ID equals 1/2 mu NC ox W over L V overdrive squared. It's just that gain without the channel length modulation effect. VA would be a unit of volts, and sometimes you'll be given that. It might say, the problem statement might say VA is 12. But other times you'll be given a number that's, say, 8 volts per micron, in which case you're getting VA prime, and you need to multiply by the channel length of your transistor, which would be given, or you perhaps need to find it. So keep in mind there's two different versions of that. Then we need to find GM. And we have these three equations for GM, which makes it wonderful, but also makes it incredibly confusing about which one really makes sense to use. So we have mu NC ox W over L times V overdrive, and we have the square root of 2 mu NC ox W over L times the current, ID. And then we have 2 times the current, drain current, over V overdrive. And these currents are all, basically we're talking again exactly about ID prime here. It's the current that you find with with just the saturation equation. And so we always have ID is equal to 1/2 mu NC ox W over L V overdrive squared. And you can use that to find the current, because for this transistor, for this amplifier, we should definitely be in saturation. Now remember, the small signal analysis method is you first find these two values. You find the drain current and you find R naught. So you find this drain current and you use that value to find R naught. And so then you've got GM and R naught, and you've got RD, so you can calculate everything with those small signal parameters quickly and rapidly. And so to do the full analysis, you replace the transistor with the small signal model, as I've done here, and can see it and do it. But with a little practice, you get so used to it that you really hardly even need to do that. And recall that we open up voltage sources as a short. So this becomes a short to ground. And if we had a current source, an independent current source, it would be an open circuit. And then we analyze it. So that's what I just did there. We just analyzed that circuit. So now if we had, I've got some room. If we let mu NC ox is 126.5 microamps per volt squared. And W over L is 100. It can be a big number. RD is 10K. And we have VDD is equal to 5 volts. VT is 0.7. VA prime is 25 volts per micron. and we set L is equal to 1.6 microns, and V overdrive is 0.2 volts. So a reasonable equation is which of these equations do you use? Right? We've got 3 equations, and which one should you grab and use? In fact, you could use any of them and get the right result, but I will tell you that the best thing to do is use the one that's got the least work, so you've got it all defined already. So we have mu and C ox, and we've got W over L, and we've got V overdrive down over here. So mu and C ox, W over L times V overdrive, we've got all 3 of those things. That's the equation to use. We don't have ID, so these 2 equations, we could use them, but they're going to be a little bit more effort to use because we don't have that value of ID. We would have to calculate it with the saturation equation. Now we have to calculate it anyway to find R naught, but there's not a whole lot of point in going to the extra effort to calculate it in order to find GM when you've already got these parameters right there. Might as well use that. So what is GM? GM is 126.5 e to the minus 6 times W over L, which was 100, times V overdrive, which is 0.2, and we get 2.53 milliamps per volt. Okay. Now you could use the other equations, but I just think it's usual trouble, although in this case we do have to find R naught, or I naught, ID, so and so we have to find I naught. So if we use 1/2 saturation equation, mu n C ox W over L times V overdrive squared, and put the numbers in, 126.5 e to the minus 6 times 100 times 0.2 squared, we get 253 microamps. And if we put that in to this version of the equation, or this one, or the other one, either one, we'll put it into that one. So we could say GM is equal to 2 mu n C ox W over L times ID square root of that. That equals 2 times 126.5 e to the minus 6 times 100 times 253 microamps, all to the 1/2. And if we crunch those numbers, we get 2.53 milliamps per volt. Exactly the same result that we got here, right? So that's good, that's reassuring. We got the same result. So there's nothing exactly wrong about doing it that way, but I would tell you, you should always look at what you're given and use that first. If for no other reason, then you run into the danger of rounding errors. You definitely run into the danger of rounding errors, and you may in fact cause some other errors that may creep up. So I just would look at what you've got and use what you've got, use what's given to do those as much calculations as you can. So we do need to find R naught. Let's go back to blue. So for R naught, we've got VA prime times L over ID prime. And so that equals, that VA prime is 25 volts per micron. 25, I'll just write in the units here, I don't usually, times our length is 1.6 microns, and divided by ID prime is 2.53 e to the minus 3 amps per volt. And I prefer to do it that way instead of saying milliamps. You'll get yourself in trouble if you write milliamps here. So when we do that, the microns cancel, and I'm just a little stumped because I'm not going to get the right units, and I haven't noticed that before. Why am I missing? What am I missing? Oh, well, of course, I don't have. I put in the wrong value here. I put in GM, but I need the current here, which is 253 microamps. So I should pick some different values so I don't get exactly the same number. 253 e to the minus 6 amps. Okay, now it's going to work right. And we put those in, we get 158 k ohms. And so if we put those numbers in, if we look at R naught parallel with RD, we've got 1 over 158,000 plus 1 over 10K. And that parallel resistance is 9405 ohms. And so we get a gain of minus 0.00253, that's GM, times 9405. We get a gain of minus 23 volts per volt. If I put those units there, they'll cancel off nicely too. If in this case, if this value of R naught is quite large compared to RD, and if we ignored R naught, so that is AV is minus GM RD, if we put those values in, we'd get minus 25.3. So that's definitely a different error, or a different result. It's about a 10% error between these two. Sometimes that might not matter, but it's usually easy enough to put them both in and get those results without much trouble.